3, Class 4, Part 1. Motion in space, 11.7. Position, velocity, speed, acceleration. Everything is the same as in Calc 1, except now we use our vector-valued functions. We are going to use derivatives and integrals to go back and forth between them. We are going to use the magnitude of the vector to calculate the speed from velocity. And then we're done. So we are going to define position as our vector-valued function r of t, which had parametrization f of t, g of t, and h of t. And then, why is it so quiet here? Oh, Matt. That's why I'm sad. Then we have the velocity of t, which is going to be the derivative of the position function, and that's going to be f prime of t, g prime of t, and h prime of t. We learned last class that we differentiate component-wise each one of these. Finally, we have the acceleration, which is the second derivative of the position function, meaning second derivative of t of f, second derivative of g of t, and the second derivative of h of t to find acceleration. And off of the velocity, the speed. Oh, I forgot to write these actually. And off of the velocity, the magnitude of velocity, which is going to be the square root of f prime squared of t plus g prime squared of t plus h prime squared of t, is going to be speed. So speed is the magnitude of velocity, which means no direction. That's why it says speed limit, and you hopefully go with the flow on the highway. I'm also going to say here that we can integrate dt to go back. So if you integrate acceleration, you will get velocity. If you integrate velocity, you will get position. Now we're going to take a look at the motion on the circular motion. So we are working on a 2D case now, which is a circle, you draw on the floor. It's very interesting to realize at one point in your life of how silly everything is out there, because we pave over certain parts of the land, and we draw some lines, and everyone is very concerned to stay within those lines, right? It's just a drawing on the floor, if you think better about it. So we're going to do just that. We're going to have a circle. Let's do the. By the way, I practiced drawing these circles. I became really amazing. And this circle has radius of 5 units. Can anyone tell me what is the parametrization for this circle? What is R?
5 cosine t, 5 sine t.
Very good. Very good. 5 cosine t, 5 sine t. Could it be 5 sine t, 5 cosine t? If yes, why? If no, why? The question is, so Mary said it's 5 cosine t, 5 sine t, and I said that's correct, and we wrote it down. Now my question is, can we have this circle to be 5 sine t, 5 cosine t? Wednesday. As good as yes or no without explanation. Or purple. The answer is yes. Yes. No, I was just trying to see if anyone is going to answer quickly. So the answer is yes. We can. It's going to change the direction, the orientation of the curve. With the cosine first, we have the orientation counterclockwise, which is the default orientation to go around. If you have sine first, the only thing it's going to do is going to switch the direction, and it's going to be clockwise in that case. So that's the difference between the two. You can use one or the other, but we use cosine first because it agrees with what we like in mathematics. All right, so now we're going to find the derivative. We're going to find the velocity. So r prime of t is the velocity vector of t, and that is going to be what?
-5 sine t, 5 cosine.
Great. And then we're going to find acceleration. Which is what? Perfect. So now as we look at this particular circle, here is t equals to 0. And I would like to compute all of the vectors, all three vectors that are concerned with this. And I'm going to use three colors. I'm going to use black for position. I'm going to black for position. I'm going to use red for velocity, and I'm going to use blue for acceleration. So now we compute these things. T equals to 0. So for t equals to 0, we plug everything into r. So 5 cosine of t is 0. Cosine of 0 is 1 times 5 is 5. So at t equals to 0, we have 5, 0. Which is this vector, 5, 0. Showing us where the position, where the particle is. Let's say we have a particle that is traveling in the circular fashion. Then we compute the red one. and the red one is the velocity, and that one is going to be 0, 5. Now we know where the particle is. We draw the velocity off of the particle, and 0, 5 looks like this. Remember that vectors are free to move. So the original vector 0, 5 would be here. But since they're free to move and I want to show the velocity of the particle itself, the position points me to where the particle is, and then at the particle I'm going to draw 0, 5 vector. And then I would like to compute the acceleration. So acceleration is going to be negative 5, 0, again from the particle, because particle is the one that accelerates or decelerates. So from the particle I draw acceleration vector. We can repeat this procedure for pi over 2, for instance. So for pi over 2, I have cosine of pi over 2 is 0, so it's going to be 0, 5. So this is the r of t vector. Then we compute the red one, which is the velocity. Velocity vector computed at pi over 2 is going to give us negative 5, 0, which is here. And then acceleration, similarly as before, it's going to go this way. And we will have this repeat itself for every case. Now, we can compute this at any point. So even if you come up with any random one, doesn't really matter. Let's say here. We will experience the same arrangement of vectors. So no matter where you draw, it's going to be the same. Now we pick the easiest ones, obviously, because they're easy to compute. What do we learn from this graph? Anyone? Just crickets on the other end. So observe which way the acceleration goes, inwards, right? So the particle is accelerating, maybe wants to spiral in, but look at the velocity pushing out, right? So when they are in perfect balance, this is what you get, circle. And with small distortions, we have elliptical orbits, we have these kind of things. You can build this up into 3D and understand why planets and large objects like stars and planets have circular shape where the galaxies are disc-shaped. We don't see galaxies ever be a ball-shaped object. They're all disc-shaped. You can have the spiral in, which is be the, not uniformly, but uniformly like space disc. This concept plays the role in understanding that, actually, on the large scale. So, no matter what kind of R you get, you will always be able to graph that, and then you will always be able to take derivatives because each component is the independent derivative, and you can graph them all. What's important is to understand that the velocity is always going to be tangentially moving tangential to the particle, and that is the preferred motion. But as you can see, acceleration pushes inverse, this one pushes that way, so the particle curves. When they are in perfect equilibrium, the particle stays trapped in the orbit. Now, can you knock it off the orbit? Of course. If you hit it with a force that is significantly strong, to overcome one of the vectors, it could spiral in or it could spiral out. So we can knock it out of the orbit. Yes. Because there is not enough, it's not clustered enough in terms of density. Because the solar systems are far apart, and you don't have enough of the forces. For instance, when you have a third-dimensional object, let's see how we're going to do this. You have a pile of rocks, right? You have a pile of rocks, and then the rock on the bottom supports the rock on the top. The rock on the top is pulled by the gravity down, and the action-reaction is when this top one pushes on the one below pushes up. There is pressure between them as well. So now think more rocks below. The one that's on the bottom is pushing all of the rocks up, but the pressure is high enough to push back. So you have, and then sideways as well. So if you have an object that is not spherical, but it's large, and you have the forces where the gravity is actually significant force. And in this case, I mean, gravity is the weakest of all forces, but for the large object, it is large enough. So what happens is that each individual block is pushed down by the gravity, but the reaction force is pushing it up to stay still, and you have the blocks on the side. So they actually all distribute evenly, and because every single object wants to be in equilibrium, which means because that's the state of the lowest energy. If the object is in equilibrium. So every object wants to be in the lowest energy state, and that means that the forces coming from sides need to balance out. The forces coming from up and down need to balance out. You have the pressure, you have the gravity, you also have the sideways pressures from each end. So when they all balance out, what happens is you have to get the sphere, because that's the only way to have perfect distribution of energy to be balanced out. So each individual, not the particle, but let's say the building block of that sphere is lowest energy state. It cannot happen for galaxies, because galaxies are far apart. Sorry, the solar system within the galaxies are far apart, so they don't cluster on top of each other. They cluster on the side, and because they spin for spiral galaxies, the spin creates this effect for the disk, and then all the galaxies stay in the disk. So you will see that all of the galaxies are always disc shaped, whether they're spiral galaxies or just uniformly shaped ones. where the planets and stars and large enough asteroids are going to all be spherical in the nature. And those are the only two shapes you actually have in the universe. So there are no other shapes, it's just disco-spherical. And that's why mainly we study those two, because right, I mean you can make triangles and squares, but you're not going to find a square planet. Because those edges at the end, even if it started with a square, this is a square, perfectly square planet, right? It's so funny if they got it wrong for Star Wars and made a square Star Destroyer. That would be silly, because it would actually collapse on its own. It will sphere itself out. Let's put it that way. All right. Happy with the answer? I hope you are. All right. Good. Good. Can you please, guys, calculate the speed? Yes. Sorry? Actually, no, we're going to make this power.
Oh, yeah.
Yes. Whoever tells you to go 4, 5, 6, please point the fingers now. And then we can later explain why I will try to repeat. But they're better. So what's the speed? Hey, NGID is here. Good. How are you doing? We're calculating the speed right now. That's how it is. Unless it's fine.
Oh, somebody was like a semester ahead of me. Oh man, so he just passing me down all this stuff. No problem. Yeah, like much laughter. I didn't even show up. Just wanted to sign
All right. Let's calculate the speed. So what's the speed? What do we have? 5. Well, I did not specify units here, so you can put miles per hour, kilometers per hour, light years per hour. It would take forever. Light years per year. So it's just light. Yeah, you simplify. Okay, so we have the speed is the magnitude of velocity vector, which means the square root of -5 sine t squared plus 5 cosine t squared. And then when we square this, we get 25 sine squared t plus 25 cosine squared t from where we factor out 25 and then kick it out in front of the square root, we get 5 square root of sine squared t plus cosine squared t, which is, right, the identity, that's 1, so we get 5. Units, which is length per time. We can do that. As I mentioned, we can do this for any shape that we want. So we can also consider the straight line motion in space, which would have constant acceleration. Let's take a look. So if we have r, so let's go with the line. R of t is given by the parametrization, hopefully you remember, x0 plus at, y0 plus bt, z0 plus ct. And what we do now is to find the velocity. We are clearly going to have just vector a, b, c. And to find, so that's our velocity. And to find the acceleration, r double prime of t, it's going to be 0, 0, 0. And this is what we have for our straight line motion. So acceleration is 0, and we have the vector a, b, c. Remember that was the one that was like a slope, right? Now, the next concept, which is two-dimensional motion in gravitational field, is something that you guys covered in your rudimentary physics class, and we are not going to learn anything new. We are just going to take the two formulas that you learned on the separate occasions in physics class and put them together in the same vector. Right? One equation, comma, the other. So we're not learning anything new. We are just technically creating a vector-valued function out of those two formulas. So Newton's second law, two-dimensional motion in gravitational field. So Newton's second law says that mass times acceleration is equal to force, but it's actually equal to sum of all forces that are exerted at the object. So mass times acceleration is equal to the, let's put sum of all forces. Here's your summation symbol that you wanted so badly in this course. It's probably going to see it now, and I don't know if we're going to use it ever again. Happy? what are we talking about here? If you have a, let's put a crate. It's not a crate unless it has the edges and things. So here. It's a crate. So if you have a crate, the crate is going to have a weight that's pushing down. It's going to have the normal force pushing up. If the motion of pushing the crate with the force is this way, then the friction force is going to be here. And the friction force is given as the kinetic coefficient of frictions times the normal force. So, and then if there is no incline, we have the x direction forces and the y direction forces separate from each other. We don't have to use trigonometry at all. So we can quickly come up with the overall equation for mass times acceleration, sum of all forces. So we have mass times the acceleration is equal to, and the sum of all forces would be force minus the friction force. In this case, so ma is equal to the force minus the mu k n. From where, because you know the mass of the crate, which is something you can always measure, you can figure out the acceleration, which is F minus mu k n over the mass. So you can find with what acceleration the block moves as you push it with the force. Now you can vary the force, you can use the integral and so on. So from this picture we see that the weight, which is computed as mg, mass of the crate times the gravity, it's easier to push this crate on the moon. It's going to be the velocity and the normal force are the same with the opposite sign. So technically this n over here is the weight. And the weight is mass times g, so you can cancel, well no you can't because of the, don't worry about it. So that's that. Now this is the block that moves along the crate. And we can make this problem more interesting, or maybe you might see it as the more annoying, if we put it on the incline, and then you have to use some trick and chase some angles to figure out which way the forces go. Now that's for physics, it's not going to be for this class. Don't panic yet. What we would like to be concerned with is the situation when we throw objects. And all of the objects that we throw exhibit what kind of motion? Yeah, when you make a projectile, you have a parabolic motion. So no matter what you throw, I'm going to dread this because I'll have to go fetch it, but everyone ready? I'm going to do this exactly once. Everyone ready? Don't worry about it. I'm excellent shot. See that? So the motion, cat-like reflexes. That was the motion that marker that is lost forever exhibited as I threw it. So we have two equations that govern this motion. There is going to be some initial vector v0, which is at the angle theta with the Mother Earth. There we go. And that vector v0, which is the velocity vector, will have the components of u0, v0. Those are not vectors, those are the components. We are going to have That's the object that's going to change the position. That object is going to have the force, which is the weight. Maybe I should use W, which is 0, and then minus mg, because that's the force that it's pulling it down. And this is V0 is the initial state, and then we have the final one when it lands on the other side. So what's ma equal to? Is equal to force, and the only force, and this is acceleration, and the only force that we have is 0, negative mg. So we have components of acceleration. If we divide both sides by m, which is the mass of the object, which stays constant at all time, we get that the acceleration vector is 0, negative g, which makes sense because that's the only acceleration that you have. You haven't seen that marker use any kind of external propellant to go further, right? Airplanes use that, right? We don't toss airplanes from one end to another, from one airport to another airport. They actually fly there, right, using their own jet fuel and engines. But if you throw something, the only acceleration that exists there is the acceleration of gravity. And as the object goes up, the gravity slows it down, and then at the top at the vertex of the parabola, the object stops completely, and then the gravity is going to start pulling it down, and then it's going to start accelerating as it goes. So velocity goes like this. At the initial point, you have the maximum velocity, which is your initial velocity, and as soon as you release the object, it has the maximum velocity possible for that trip, and then it starts slowing down as it climbs. When it reaches the vertex, which is the maximum height that the object will reach, the object has the 0 velocity, and then it starts falling because the gravity starts pulling on it, because it's so high up. The gravity is pulling on it, and it starts picking up velocity again, and then eventually it lands. The velocity at the impact is called the impact velocity, and that's the one that it's in charge of breaking things. So you don't break things because you drop them or throw them or anything. You break things because you don't break things. It's the nature that breaks things. So you just, don't feel bad. I wish I knew that when I was 5 years old. So all these concepts, they come in so late in life. Many unpleasant days would be much better if I knew that, to explain how I had nothing to do with it. That it was the actual impact velocity that was fatal for the vase. Now, what do we know for what do we know in life for these things? We know that if we have acceleration vector, we can integrate that acceleration vector and get the velocity vector, and then we can integrate one more time to get the position vector. So if I start with acceleration vector, which is given as 0, negative g, and I integrate both sides in terms of dt, we are going to get that the velocity vector in terms of t is going to be some kind of a constant, right? Because when you integrate 0, you get 0 back. But you are going to get plus c, which is the constant. So there's going to be some kind of constant there. What do they call it in the book? U0. And the other one is going to be negative gt plus v0. Now, maybe I should just go and note that this thing is like your plus c. So now you know that that plus c from all of our years of screaming, it's not there for decoration, it's not there for decoration. Well, now you see it at work. So now that I have my velocity vector, I will copy it again and take another integral there. Another integral dt. And as I do that, we get the position. In our case, we use r. And that's going to be u0 t plus, again, you need to have plus c, right? So it's going to be some kind of constant, and they like to use, well, they use plus capital C, and then x0. And then for the velocity, when you integrate, you get negative 1/2 gt squared plus v0 t plus y0. You know both of these formulas from your basic physics class. You know that your final velocity is equal to initial velocity and then whatever modification you have from acceleration term. So you may be remembering this formula from your physics as V final is equal to V initial plus AT, if you remember your kinematics at all. And over here, you can clearly see parabolic motion because here is your negative x squared plus x plus a constant, right? So that's a parabola. And it's a downward opening parabola because it's negative, right? So we have that arc. You cannot escape this physics. And by the way, that's how much Newton did. At his time, there was no exponential functions or trigonometric functions or logarithmic functions. Technically, you know more than Newton now in terms of this stuff, right? Because integration is after Newton. But he did know how to do some antiderivatives because it was just a property backwards, but there was no e to the 3x dx. You hopefully all know how to do that also. There you go. Congratulations. Yes.
What's UO?
It's defined over here. You wrote somewhere. There you go. It's the initial velocity component. So initial throw. That marker over there that's close to us had the initial velocity when I tossed it. So from this formula, you have the x directional motion and you have the y directional motion for and decomposed. So in your physics courses, you compute one separately from the other, and then you bring two equations together to calculate the common time or something, to use one equation to compute something and then plug into another and so on. So that's the, this is, as I said, you know these formulas, both of these formulas, you know them from physics. Now we just put them together into a single vector, 2D vector, and we call it the, what's the position? The vector valuing function for position. And done deal. And then they have the flight of the baseball example, which you can read. It has all these letters and numbers and uses this formula. They also talk about the range, the flight time, and maximum height. Maximum height happens at velocity being equal to 0. So all you need to do is to differentiate this, which is when you get this, and you set this equal to 0. Now you can't set that one equal to 0 because that's your initial velocity in x direction. But this one you can set equal to 0. This is not 0. This is not 0. So these two will govern at what time you have the maximum velocity. And, sorry, zero velocity, which is the maximum height. Also, for those of you who are good with calculus, you know that when you take the derivative, right, you get the critical points, which are minimum or maximum. So that's another way to understand. So if you have the function, you differentiate to get min or a max. In this case, it's going to be max because it's downward opening parabola, and then at that point is going to be, at that time, is going to be maximum height. So for maximum height, the velocity in y direction is 0 because the object was moving up and then stops and then starts falling down. Now, you don't see that well when the object does this, because why would it say that the object stopped? Because it never stops. But actually it does. You see, that for the velocity vector, the x component of the velocity is always constant. So that's why there is one uninterrupted path. But if you look, you know, when you throw a marker, if you throw it in front of yourself, you will not have the perception of the arc. All you're going to see is when you throw it, it's going to go up and it's going to go down. When you look straight at it, if you throw it in front of yourself, and that's going to be this. So in that point, you will only be observing the y motion, and the y motion will do with the marker go up and go down. And you will actually, in order for you to go from positive to a negative velocity, right, because it changes direction, you have to do that through 0. So it has to stop and then falls. Where the x direction of motion is always constant, going forward, going straight. And you probably did like 5,000 problems with this. So, there you have it. And as I said, even though this is a rudimentary physics that every single one of you should know regardless of the major, because this is over 400 years old, and you do throw things around, whether you're annoyed or just like to do it. These formulas will still be given to you on a test if something like this pops up because it's, you know, physics. And then we have the same thing for the third-dimensional motion. But for third-dimensional motion, you have to be a little bit careful because you will have to actually figure out where this motion is going to happen. See, if you have x and the y-axis as we agreed, and the z-axis in the corner, and you toss something from the corner, let's say diagonally, in the classroom, you are not going along x-axis or y-axis to have xz or yz, which would use these formulas, just rename them a little bit. You will have a combination of x and y. So they don't dwell too much in the book on this because much more powerful techniques are coming up in linear algebra for rotating the coordinate space, coordinate system. So over here, you have to go through additional hoops to figure out the parametrization of the path and then adjust the equations so that when you throw something, because you're not on x-axis or on y-axis, it can, you know, it goes where it's supposed to go. In linear algebra, what you do when you have something like that, you figure out what is the angle, and then you multiply by the rotational matrix to adjust the coordinate system, and then you can end up on x or y-axis and just use these equations out of box. Learning linear algebra is fundamental for most of you guys in terms of especially computer science to understand. Now, obviously, mechanical engineering, electrical engineering, I mean, without linear algebra, just dead in water, you have no clue what's going on in the world. I'm not sure for biomedical, have a lot of bio people here. But unless you go high-end research in biomath, if you do neural networks, then linear algebra is one of the most important ones. So, do you ever have a class with Robert Miura or no? At MJT? No? He's one of the living gods of mathematics. So, yeah. Do what? You took only one math class. Wow. I'm honored. So you took... Yeah. Well, we don't. All right. Guys, that's motion in space. You know it from before. Take some derivatives, take some integrals. Done. We'll stop the stream, go for a break. When you come back, more cool stuff.